Welcome back to the third and hopefully last part about detailing the usage of these HB100 Doppler radar modules, Limpkin's amplifier boards for them, and making sense of the amplifier board output with an MCU, the trusty Arduino Nano, which I have here like last time on a stand, measuring down the room, and we saw it does pick me up walking back and forth, but as you can see here, there's a lot of noise in the signal, and if I step to the side for just a second and hold my breath, the sensor is picking up something, but there's nothing. There's absolutely nothing. And we'll try to solve this by using the second output of the Limpkin amplifier board, which is a signal level out. So let's try to get that into the picture. I whipped up some code to show the VOUT output, so the signal level output from the amplifier board via the Arduino in the Arduino serial plotter. It's the red line. And as you can see, as long as I'm waving around in front of the sensor, the signal level is well above 240. But we will have a look at the code and what that means in a second. But anyway, if I remove my hand and sit very still, the signal level drops and it drops and it drops, until we are somewhere between 120 and 140. And as soon as I move into the picture again and wave my hand in front of the sensor, our signal level is up. And I'm moving my hand out here now. If I'm a little bit away, you see the signal level is dropping a wee bit, not much, just a wee bit in between. But so we definitely can use that signal sensor to eliminate noise. But let's have a look at the code now. If you haven't seen part 2 yet, now would be a good time. Okay, card here and link in the description, because there we developed all that code and I will only explain the changes I made. We will do 2 passes through the code, because there's the standard version and then there's the version with some bit banging. Anyway, I have a new constant here, constant byte, HB100 VOUT pin. That's my analog 0 pin where I'm reading out the signal level from the amplifier board. I also have a new global variable, volatile byte pulse levels. That's again a ring buffer where for every pulse I get, I also sample the pulse level or the current signal level. And it's a byte. I'm using analog read later on to get that analog voltage into the Arduino, but I'm scaling it down to a byte. Reason being, I've run out of RAM. Okay. Besides, the ADC function of an Arduino are not that precise, and we don't need any precision here. In the setup, that pin mode for the VOUT or voltage out pin of the amplifier is input. And the next big change is in my interrupt routine that records each pulse we get from the amplifier. And there I'm now also recording the pulse levels with, as I mentioned, the analog read function, which I scale down. Yeah, this is normally on a nano 0 to 1023, and I scaled that down to 0 to 255. So yeah, it will fit into my byte array. Then in my main loop, besides the pulse times, I also get the level of my current pulse from the pulse level array. And all I do with that is, it's a second value I'm printing out on my serial port and then via USB display it in the Arduino serial plotter. Now on to the second path and the bit banging I do. Normally that analog read from the Arduino gives you about 10 kilosamples maximum, and one single analog read operation takes up 0.1 milliseconds, about-ish. Now if we have here 100 pulses per second and call that here 100 times, 0.1 milliseconds becomes 10 milliseconds, okay? And yeah, I don't want to waste that much time here, and I don't need, as mentioned before, and as we see here, not a 10-bit accuracy, which, the Arduino ADC doesn't provide anyway. So I'm using code from, YAP Arduino Blogspot to change the ADC sample rate of an Arduino. And I won't explain that in detail, but you need here two macros to clear a bit in a configuration register and to set a bit in a configuration register. And later on in my setup, I obviously set a bit in one register and I clear 2 bits or 2 bits in the same register, and I'm changing the sample rate from 10 kilosamples per second to 1 megasamples per second. Now you cannot do that without some penalties, okay? You will lose 1-2 least significant bits of accuracy, if you can call it accuracy. I mean, I did some videos about external ADCs, cards, links, or one card and one link, where I also talk about the performance of the internal Arduino ADCs. Anyway, that's a big banging motivation. I don't need the accuracy, number one. And number two, I don't want to spend really over an additional 100 microseconds in my interrupt routine. That's no good, spending much time in interrupt routines. And at 1 megasample per second, I only spend an additional 1 microsecond in the interrupt routine. That's acceptable. If we want to understand that VOUT signal, we have to take a step back and look again at the circuit diagram of Limpkin's amplifier board, link in the description. And I won't discuss all details of the circuit diagram again. We did that already in part 1 of this series. Card and link in the description. The last amplifier stage of our second order bandpass filter goes also into a diode peak detector. The diode, that resistor, and that capacitor here, 10 micro. And here is the first problem. There is no resistor here. That is the only load on that 10 micro capacitor to get, the voltage down again is the current that is drawn through the Arduino input, analog input pin. That's quite high impedance. So that's the reason why we see the signal level dropping off slowly. The second effect here, that the signal level was always between, even if there's nothing happening in front of the radar module, between 120 and 140, is that the last stage, this inverting bandpass filter, the positive input of the op-amp is bound to 1/2 VCC. So if we have no input here, the output will be at 1/2 VCC, that is 2.5 volts. And so we never get to 0. Just some things to keep in mind, and I really want to make that VOUT output go down faster. Here's the relevant circuitry again. We have our analog signal somewhere up here, centered around 2.5 volts. Then we have our diode peak detector, and that goes currently into the Arduino. And the Arduino input impedance is about 100 mega ohms, though on an analog input, if you are sampling, there's a switch which will charge up a 14 picofarad capacitor. But that's okay. 100 meg, 14 picofarad, 10K, 10 microfarad. We'll forget about that here. Anyway, I want to add a resistor here to discharge the capacitor, the 10 micro, a wee bit faster than it does naturally. And you know the time constant for an RC element is tau equals R times C. And if we want to know the resistor we need for a certain time constant tau, it's that formula. And I want to shoot for a time constant of 250 milliseconds for the discharge. So we have 0.25 seconds over 10 microfarads is equal to 25 kilo ohms. And I don't have 25 kilo ohms resistors, so I take a 27 kilo ohm resistor. And I will put that on the breadboard now, and then we have a look-see. I will probably need to make the resistor a wee bit bigger, but that's a good starting point here. Actually, I'm quite happy with that 27K resistor. It resides right there. Anyway, the voltage level or the signal level dropped, of course, in our plot because, the 27K resistor and the 10K resistor, they also form a voltage divider, but that's okay. Anyway, if I wave my hand in front of the sensor, we get a nice high signal level at about 160 now. And if I'm very still, the signal level drops to, I don't know, 80, 90. That's the noise level. And if I wave my hand, a little bit further out, we get a slightly lower signal level, but not that you could really estimate the distance there, but being still again. And it drops really fast, okay, so perfect. That's really perfect. So let's use that to filter our velocity signal. So I modified the code and I'm quite happy with the result. So you see there I'm waving my hand and I get some velocity signals, of course, very convoluted. And the signal level is up. By the way, the red line is the signal level. I scaled it down by the factor of 2. So we have a little bit more resolution here on the screen for the speed signal. But if I move my hand, and this is off camera, in a very consistent and slow way, you can see I get a consistent, I stopped, I'm approaching again. I get a nice consistent stopping, moving away again. Stopping, approaching again, stopping, and yeah, to really hold the hand still in front of the sensor is not quite easy. If I just, yeah, wiggle a finger, you get a signal. Anyway, let's have a look at the code. Okay, I have a new constant here, constant byte level minimum. Yeah, minimal signal for analysis. And after some experimenting, I set it from 100, which we observed, to, yeah, instead 120. The reason will be clear in a second, because we simplified our code. And then in the main loop, I have now another byte variable here, level previous, because I'm not only looking at the level of our current pulse, but also at our previous pulse. And analog to the level current, I retrieve the level previous from our level ring buffer. And then I extended simply our sanity check here for the signal by these two level conditions. So the current level has to be greater than the level minimum, and the level previous has to be greater than the level minimum. Please note, if you would do that correctly, you would somewhere here loop through all the pulse levels. I mean, we're looking here at 4 pulses each time, and check for the level of each pulse. But yeah, check the current one and the first one in the series that we are looking at. Good enough for now, or for this video. Yeah, increasing the the level minimum allowed me to get completely rid of this frequency sanity check. You remember we sometimes receive the 100 Hertz mains AC harmonic in that amplifier. Yeah, but that is obviously sometimes a little bit higher than signal level 100. So, but at signal level, minimum signal level 120, that's filtered out. So we don't need that anymore. I'm always happy if I can simplify code. And yeah, the last change was just, yeah, for scaling in the graph that I divide the level current by 2. That's it. I think it's time for wrap up with some experimentation. Yeah, you know already the name of the game. The notebook is back on the stand here. And yeah, the serial plotter is running. The radar is pointing down the length of the room, and I will walk up and down, and we'll see what kind of signals we will get this time. You already know that lid of a tin can from, I think it was in the first video. Didn't use it in the second video when I was walking up and down, but yeah, just to give you an idea of maximum signal levels. I mean, sheet metal is a good reflector. I'm standing here a little bit out of the way until there's no signal. Then we come in as a defined slow pace. with the lid. So yeah, that's our slow reference signal. And if I wave it faster, then we get, of course, higher velocities. Okay, putting the lid away, standing in front of it until everything is still again, and then my talking makes radar signals, Doppler signals. And then I will move slowly away from the sensor. Can you still hear me? Because I'm not wearing a microphone. Until I'm at the door. Sorry. That hurt me more than it did you, huh? Then I will take a few quick steps back and forth. Okay, very still again. Just for a few seconds, and then I will slowly approach the radar. And I got a feeling I will have to put that into captions and stepping out, sorry, of the way again, so it can. I have the feeling that it doesn't pick me up, or it picks me up at a very, very late stage when I'm approaching. I'm not sure. Let's try it again very slow with the reflector, radar reflector in front of me. I have to be very still so the signal can go to 0. I'm not talking. Okay, I can't do that because I'm vibrating here. So let's step back slowly. "21, 22, 23, waving, sheet metal." Okay, I wait again, 21, 22, 23, and approaching slowly. Let's see when the radar can pick me up again. Oh, that worked better. Obviously, it works better when you're more radar reflective. You could say, I'm stealth. No, there are other reasons for that, but let's try and I dread that a little bit to do a fast one, okay? I will not talk during that experiment. I will try not to bump into the door this time. Okay, 21, 22, 23, and approaching fast. Okay, I think we have some nice curves here, some test data, and I will annotate them, yeah, and give you some distance measurements. Waving. Oh! Speed record! Waving, measuring the distance at which the signal came back or at which the signal lost. Yeah. See you back on the bench in a second. So, what's the verdict? When I was moving slow, I lost the signal at 3 meters, and yeah, I got it back at 3 meters, but you saw, yeah, over there, the noise level in the speed signal is about 40%. When I moved slowly with a reflector, yeah, I lost the signal after 4 meters, so that little bit of metal reflector gave me additional meter. And the noise level was also significantly lower in that signal. Yeah, have a look. Yeah, guesstimate 25%. When I moved really fast with the reflector, I lost the signal only at 4.5 meters. And I got it back very late at 2 meters. But I attribute that completely to delays in the software. Yeah, we have our ring buffer and we have our averaging, and yeah. So over short distances for very fast moving objects, it's hard to get any data out with that setup. And I won't talk about the noise level because, yeah, these were only really a few data points. Talking about those noise level, the fact is that the radar doesn't give us just one Doppler frequency, but a mix of different Doppler frequencies. Because, yeah, different parts of a human being when walking, yeah, pardon the modern art, they move with different speeds, and this gets all mixed up in the output. And yeah, we somehow try to, or we are detecting the major, amplitude-wise, major frequency content. Of course, when you put a metal plate, a strong radar reflector in front of you, the signal reflected from the plate will dominate all this noisy other stuff, so your general noise level will go down. So it's much easier to measure the speed of a car than to measure the speed of a human being. Of course, considering the the reach of our little HB100 radar module, measuring cars going by is probably not gonna work. Maybe in the garage, moving very slowly. Anyway, you can always take your Doppler signal and feed it in a fast Fourier transformation, and out you get the frequency spectrum, or in that case, the speed spectrum, the different components, speed components you have in the signal. But yeah, you can do that with a real good Doppler radar, but with the HB100, which contains exactly 2 transistors, watch part 1 again, there was already a card link in description, with 2 transistors, 1 transistor oscillator, not stabilized in any way, plus 1 transistor for the mixer, that's casting pearls before the swine. So let's not do that and take it at what it is, a sub $10 radar module that with a sub $10 amplifier can give you some speed indications. Noise level 40%, remember 25%, some speed indications, and definitely movement detection within 3 meters. Regarding movement detection, one, it's the last remark, I swear it, the last remark. Don't fumble around with the frequency output of the amplifier, and if you just want to detect motion, go for the VOUT, for the signal level output, and much easier. Those were the details about the HB100 radar modules, Limpkin's amplifier boards for them, and taking the signals from the amplifier board and making sense of them with the MCU. I used an Arduino Nano, and till next time, bye!